Section 3.5 is multiplication and division algorithms. And we're going to do mental estimation in here as well. This is going to feel like the same thing we just did in section 3.4, but the operations of multiplication and division instead of addition and subtraction. So sort of the structure of this lesson is going to look a lot like the structure of the last one. The first thing we need to do before we get started with actually looking at algorithms is we need to define a couple of things. One has to do with being exponents. So if we have a to the n, this means a times a times a. How many of these are there here? Don't everybody answer all at once. N, yeah, there's n of these. This is n times. Whatever the exponent is, that tells us how many of that base we have. So we call a the base, and we call n the exponent. And the first thing we're going to look at is we're going to look at what are called properties of exponents. So the first thing we're going to do is remember, if we can, we're going to remember what those properties are. Okay? And then I'm going to actually show you why they work, and then we're going to use them. So I'm not going to ask you later on, why do these work? I'm not going to do that. But I feel like that you need to see that in case you haven't ever before, because undoubtedly one of you in some point in the future is going to have some kid in your class that's going to say, well, why do we add instead of multiply? And I don't want you to look like a deer in the headlights and go, because the book says so. Not the best answer for the kid that asks that. So even if you couldn't answer that on the spot, you could say, you know what, let me bring that back and I will show you exactly why next class. And you'll know that there's places where you can go back and take a look for that. Okay? So the first thing we're going to look at is what happens when we have a to the m times a to the n. Do you remember what you do to combine those into a single a to some power? You do. You add the exponents. Okay, so if you multiply a to the m and a to the n and you add the exponents, what do you think you're going to do if you divide a to the m and a to the n? You're going to subtract. How is 3 different than 1? Okay, but how is that different than the first one, the number 1? What's different about them? It is going to look like a distributive property, but how is that different? How is the question different looking than this one? There are some parentheses. What else do you notice that's different?
The base.
The base. What about the base, Amanda?
On the first one, both bases are a, so it's like a to n to a to n.
Okay.
On the next one, the first base is a, and then the exponent's n. But then for n, the base is a to the n.
Okay, so Amanda's right. I'm going to say it in a slightly different way. What I want you to see is that on the first one, you have the base listed twice, correct? Okay. On the second one, there is only one base. The base that is there is a all by itself. There's not a second a to some power. Do you guys see that? And the way Amanda said it's actually really good. What happens is that n right there is a power of the a to the m. And when Kaylee mentioned this looks like distribution, she's also right. It's not exactly distribution, but we do in fact combine the m and the n, and we do it with multiplication on this one. So it has this feel like somehow we're distributing. I think 4 probably looks a little bit more like distribution than number 3 does, though. Do you guys remember what 4 is going to look like? Or any guess? Yeah, this one really has the feel of somehow us distributing that exponent over the multiplication, right? Okay, so these are the 4 properties of exponents that we're going to look at in this section. In chapter 6, I think it is, in your book, which is something we cover in what used to be called Elementary Math 2. Some of you have already had it. We have more properties than just this, okay? And so some of you are like, oh, I've seen some of these before. Well, yes, you have, and that's why. So take a look with me, and I'm going to explain for us, or help you to explain, why the properties work the way they do. So this first one, what did we say we're going to do with m and n? Add them, right. So why in the world does that work? Well, I'm not proving, per se, of why this is working. I'm just giving you an example that justifies it. So we're going to do an example of a to the third times a squared. All right, what does it mean to say a to the third power? What does that really mean? Right, it means I've got a times a times a. There are 3 a's. That was the exact definition that we used on the very first slide today with n equal to 3. The exponent's 3. So then what does a squared look like? Yeah, a times a. So what is this when I have 5 of these? It is a to the 5th. And if you're making a comparison between this value and these two, what can you tell me you have to do to get from 3 and 2 to 5? You add, right? So if you were in the middle of a testing situation and you flat out just could not remember this, maybe you're taking the OGET or something and they give you a problem like this, should you be able to figure this out pretty quickly? You really should. You should be able to create an example and see which one it is. I can't remember. Is it multiplication or is it addition? Well, put some numbers in here and see which one's supposed to be. And we should be able to create one. All right, what was the second one? The rule, the property. Subtract. Very good. All right, so again, we're going to do an example. And we're going to do a to the 5th over a squared. So what is a to the 5th? A, 5 a's, right? What is a squared? 2 a's. And this is all multiplication on top, multiplication on bottom. And these are fractions. And we are going to reduce them in what way? What do we do? Yeah, so if they match, because they're factors, right? Because multiplication, I can cross them out. Basically what I'm doing is I'm dividing them out, really. And what does this leave me with? 3 a's. A, which looks an awful lot like a cubed. So again, how do I get from 5 and 2 to 3? You subtract, right? You do. All right, another one here. This one we said just a moment ago was multiplication. Let me just try it like that. So we're going to use the same thing we did a minute ago where I did a cubed and then I had a squared after that where we put the squared on the outside. You guys told me that a cubed looked like this. Does that look okay? Just replace the a cubed with a. Okay, so what does squared mean? It means multiply it by itself. So the itself that we're talking about here is this 3a bit. Okay, so squared means multiply whatever it is by itself. And if I notice then, how many a's do I have? 6. And again, how do I get from 3 and 2 to 6? You multiply. Okay, last one. This is the one we identified as looking a lot like something called distribution. And we will do this with ab to the third power. So raising something to the third power means multiplying it by itself how many times? 3 times. ab, ab, ab. Now what I really want to do, and I'm going to do it in one step, is I really want to put basically all the a's at the beginning and all the b's at the end. So talk with me about what 2 properties that I used to be able to reorganize my information in that way. It's associative and commutative. Commutative changes orders of things, right? So it switches some of the b's and a's around so that moves the a to the beginning and the b to the end. And then the associative, and in some sense, what I really have done here is I've grouped the a's together and I've grouped the b's together. And associative is what allows me to reorganize sets of parentheses to regroup things together. So those are the 2 properties that I use, and I used them like, I don't know, probably a dozen times seriously when I moved those around because I didn't physically show you every single move. You guys would get bored with that in about 2 moves, okay? But that's what would happen. And then, of course, I end up with a cubed, b cubed when I'm done. And if we compare that back to the beginning, we recognize this feeling of being able to distribute the exponent over that set of parentheses that's applying the multiplication. Okay, is everybody good with the kind of science behind this kind of thing? Okay, here's what we're going to really do with it, though, is that we're going to take examples and we're going to use those properties so that we don't have to do them out longhand. So do I expect to see you to write down 10 fives on this problem? Please do not write down 10 fives on this problem. That would not be a good use of knowing those properties, right? In fact, it would be exactly the opposite. It would be ignoring those properties. So we want to use those properties together. So these three things are all multiplied together. So taking a look at the problem set above, or even two sets above, where I have all the properties written down, what property are we going to be able to use to rewrite this? 1, 2, 3, or 4? Which one? 1. Did you guys see that? I mean, there's 3 of them, but this is multiplication. They have the same base. So what do I do with the exponents? I add them. And it works just the same way with 3 numbers as it did with 2. So this is 10 plus 2 plus 4, which gives me 5 to the what? 16. And that's all the problem's asking you for. That's it. How is B different than A? Indeed, they have different bases. Oh, I think I left out a slide somewhere in there. Oh, no, it's just further down. I'm sorry. There it is. They have different bases, don't they? But are the bases somehow related? Can you see how they're related to one another in this particular problem? I have 6, I have 2, I have 3.
3 times 2 is 6.
Yeah, 3 times 2 is 6. So there's a couple of things I could do. Let me show you one of them, and then I'll show you the other one. You can decide which one makes more sense to you. Okay? The one that I see when I look at this most easily is taking the 6 and breaking it down into 2 times 3. So this is like basically 2 times 3 to the power 4 times 2 to the power 3 times 3 to the power 3. Once it's written in that form, this should look like property number 4, a, b to the m. Do you see that? 2 times 3 to the 4th. So I can distribute 2 to the 4th times 3 to the 4th times 2 to the 3rd times 3 to the 3rd. Now, do I have some bases that match? Yes. Do they all match? Well, no. That's okay. So tell me one of the pairs that matches.
4.
Good. 2 to the 4th and 2 to the 3rd. So if I combine those, and of course I'm using the property of commutativity to reorganize them, right, to move them around. But if I combine these, this will give me 2 to the what? 7th. I'm adding exponents. That's property number 1. And then the other 2 that are left, 3 to the 4th and 3 to the 3rd, those also combine, don't they? So on that one, I recognize that as 3 to the 7th. And this is one of the 2 acceptable ways to write this as your answer. We can't combine those except for in one other way that I'll show you in a minute. But this is a perfectly reasonable way for the answer to look at the end. And in some ways, preferable. Okay, can I show you one other way to do the problem? And then as far as I'm concerned after that, you can make your pick when you're working these as to which one makes more sense to you. Okay, so we start out the same way, 6 to the 4th. 2 to the 3rd. 3 to the 3rd. Option number 2 is to recognize that both of these at the end have a power of 3. And very much the way that we can distribute, we can also take it out. So I could recognize this is already 6 to the 4th, as 2 times 3, and factor the power of 3 out. And then 2 times 3 is what? 6. And lo and behold, I have another base 6 in my problem. And then I have 6 to the 4th and 6 to the 3rd, which is 6 to the 7th. can you see how the answers here, and this is a second correct answer, are related? Sure, if I broke the 6 down, I'd get 2 times 3, and then I could distribute the power 7. Or I can take the 2 to the 3, and I can undistribute the power 7, and I'd have a base of 6. These are both valid answers, and depending on the context of what we're working with, either one could be the most useful way of handling it. Any questions on multiplication with exponents? Okay, let's take a look now with multiplications where we're not dealing with exponents. So these are the multiplication algorithms. The first one we're going to do is the standard algorithm. And after we do the standard algorithm, I'm also going to show you as a part of this the expanded algorithm. I don't have it listed, but we'll just list it beside it because they're very similar. All right, so let's do the standard algorithm first. 48 times 32. All right, so standard algorithm, the one you know and love and have used for, I don't know, probably something like about 12 years, right? What do you do first? 2 times 8. We start on the right-hand side, yeah? So what is 2 times 8? 16, and we do that. What do we do when we do 16? Write down a 6 and we carry a 1, which looks a little mysterious, but we've talked about this carrying 1 bit before, so I'm kind of okay with that. Right? If we've got the carrying 1 bit from addition, we're probably all right with that piece. What do I do next? 2 times 4, which all of a sudden looks a little weird because we didn't do anything like that with addition, right? Now we're like off sequence in terms of which values we're working with. All right, so what's 2 times 4? 8. And then what do? You mean I add in the middle of multiplying? That's awkward, isn't it? A little awkward? We were multiplying and now we added something in the middle. Okay, so what does that give me? 9? Is that what I have? I was talking too much. I wasn't paying attention. 9? Okay, good. Now what? Okay. We put a 0 in here just for fun, right? A little bit magic going on. We got a lot of magic going on. We've moved some things around. We've added in the middle multiplying, and now we have a 0 show up out of nowhere. All right, so then after we show up our magic 0, what do we do? 3 times 8, which gives me 24. So what do I do with 24? I write the 4 down. Oh, and then I change this 1 that was above here to a 2, basically, right? So I do this carrying 2 bit. Again, we might be okay with the carrying 2 part of that, but then what? 3 times 4, which is 12, and then in the middle of my multiplication, I'm going to add 2 to give me 14. And then, as if I weren't already done enough, because I've done quite a bit at this point, I'm going to add again, right? Yeah, and then I'm going to put a 6 here. I've got my 3 and carry my 1 to give me 5, and I have 1536. You guys don't even feel like it's weird until I started saying how weird it was. But do you see what I'm saying about how many steps and how odd it feels in the middle of this problem? It's really awkward. So let me show you the expanded algorithm, and this actually looks a little bit like the one that you were asking about, Kaylee, from the section C. When I do the expanded algorithm, I'm not going to expand it the way that I did before. I'm going to expand it like they did in the book on that problem. So instead of writing the 48 as 48, I'm going to write it as 40 plus 8. And instead of writing the 32 as 32, I'm going to write it as 30 plus 2. So basically, I have 4 numbers here. And it might even help for me to write it like this, based on what we just recently did in some homework that you had. 40 plus 8 times 30 plus 2. Because that starts to look like we could use something called what? What property? Distribution, right? What did the distribution property look like? Some of you got some notes on your papers when I was grading this one where I said, show me more details. Because what you really did is you FOILed something out, which is distribution, but you combined things in the middle of doing it and so forth. So what I was looking for is something where you say 40 times the 30 plus 2 plus the 8 times the 30 plus 2. So you're distributing one piece at a time. And then you're distributing the 40 times the 30. I'm giving a lot of explanation that if you did this, you wouldn't show all these details, but I want you to see where things are coming from a distribution point of view. And then you'd have your 8 times your 30 and your 8 times your 2. This gives really good justification for why I multiplied 4 times. Because look back at the original problem. You guys had me multiply 2 times 8, and then 2 times 4, and then 3 times 8, and then 3 times 4, right? You had me multiply 4 times. Well, why? Well, because that's what happens when I distribute. I actually end up with 4 sets of multiplication. So let's actually do this one out, and then I'm going to show you a cool, I think it's the next one. Yeah, it's the next one. I'm going to show you a cool visual for this. All right, so what is 40 times 30? What is 4 times 3? 12. And then what happens when I multiply with zeros? I get that many zeros when I'm done. So this is 1200. What is 40 times 2? That's 80. What is 8 times 30? 240. And then 8 times 2? 16. Now, we could write that vertically if you want. I'm not too terribly concerned about the addition. We've already talked about the addition on how we add these things together. We are, of course, going to get the same 1536 that we got before by adding these 4 values together. Now, writing it all out in that fashion is not terribly efficient. But let's use this same idea on the next example, and I'll show you a way in which it is more efficient. And it also has, oops, sorry about that. It also has a really good visual that goes right along with it. This is called partial products. Partial products uses a square grid. And we're going to make it a grid. And what we're going to do is we're going to write the 48 as 48 like this. Okay, so it's still the 48 we saw before. We're going to write the 32, and it doesn't matter whether we write it on the right or the left, but because of what I'm about to do in a minute, I'm going to put it on the right-hand side. And what we're going to do is inside every box is going to be the product of the row and the column that we're on. So this top left-hand box is really 40 times 30. Now, I'll show you a picture of this that actually makes more sense about why this is helpful in a moment. Let's just fill in the numbers because this is the efficient version of what this is doing. These are all the same numbers we had before. So 240 here, I have 80 here, and I have 16 here. And then in terms of adding these together, I'll write it out this time. We have something like this. I'll do standard algorithm here. This is a 2. I have 4 plus 8, which is...
Wait, why did you put 2 on the bottom?
Oh, because I don't see all my screens at the same time. How about a 16? Will that make you happier?
Yeah.
It'll make me happier too. So that's a good idea. So let me write a 6 here then. All right, let's do 4 plus 8 plus 1 then. 13. So I'm going to write down a 3, and I'm going to carry a 1 because that 1 is actually representing the number 100. Then I have 100 plus 200, which gives me 500, or 5 in the hundreds place, and then my 1 that's down here at the bottom. So it's 1536. Let me draw you a picture of what this is really doing. We've had an area model for multiplication before, right? Here's 40 wide, and here's 8 wide. Is that believable? It's more believable than my other diagram where they looked equal, right? And then the other one is 32. So here's the 30 long, and here's the 2 long. This is an area diagram of exactly what's going on. This top corner right here really is 40 wide and 30 long, so it is 1200. This one over here really is 8 wide and 30 long, that's 240. And so forth in the other two diagrams boxes. The partial product one that I wrote before is just allows us a placeholder in which to put it. But we can start by taking a look at that diagram to justify why those numbers are actually working for us. And they're working for us because they're representing that area diagram. This one is probably my favorite in terms of justifying why in the world we really are multiplying all 4 values together. Because the area diagram is so visual, and I think very visually. Let me show another one. This one is actually my daughter's favorite. When she was learning to multiply, my 10-year-old, The standard algorithm was really confusing to her. She's fine with it now, she has no problem with it, but she was really getting, it wasn't making sense to her, this carrying and adding and multiplying in the middle thing. I mean, it just wasn't connecting. So I showed her this one, and her teacher freaked out a little bit because she had never seen this before. And so this method is really cool. It's called lattice. Now, you've seen lattice before with addition, so now you're going to see lattice with multiplication. So we're going to put the grid. I'm sorry, I should have started with a grid. You need a grid. It's going to be just like the last grid we had. Okay, a 2 by 2 grid. We're going to put the 48 here, but we're going to actually put the single digits of 4, an 8, and a 3, and a 2. Okay, so along the top and along the right, and we really do need it along the right. If you put it along the left, it's going to run into some other stuff, and that's not going to be helpful. So along the top and along the right. So with the lattice method, when we did addition, what we did is we took all of our boxes and we split them along the diagonal like this. So far, so good? All right, and just like what we did when we did addition, we did the row and the column and we added. Well, now we're going to do the row and the column and we're going to multiply. So we can do it in any box we want to start with. I tend to start with the top left box. So the top left box is the number 4 on the top and the number 3 on the right. 4 times 3 is 12. And so just like with lattice addition, we put the 12 where the tens value is in the top corner and the 2 value is in the bottom corner. And we're going to do this for every box. So the next box, if I'm moving along the top row, would be 8 times 3, which is 24. So we've got a 2 here and a 4 here. And then I'm going to keep going left to right because that's kind of how we read. If I go again, I've got 4 times 2, and that's going to be 8. 8's a single digit, so it's just in the bottom corner down here. And then I have 8 times 2, which is 16. So I've got a 1 in the top and a 6 in the bottom. Do you remember what we did when we were working on, hang on, I want to get a highlighter out. What we were doing when we were working on this last time with addition. Yeah, I put these yellow marks in, and I said we're going to be adding along diagonals, right? And that's exactly what we're going to do here as well. And we do need to start in the bottom right corner. So the bottom right corner is always going to be the number that's already there. So that's the 6. And then we're going to go to the next yellow diagonal. I've got a 4, a 1, and an 8. The 3 that's on the outside does not count. That was part of the multiplication that I had. It was one of the factors. It's not part of the products. So we're only adding the 4, the 1, and the 8. And 4, 1, and 8 is going to give me what? 13. So I write the 3 down, and I carry the 1 up here. So now I've got the 1 that I carried, the 2 and the 2, which gives me 5, right? No carrying involved. And this 1 right here on the top is 1. And my answer then is right here at the bottom. It's 1536. There's several benefits to this. One of the benefits is that I'm multiplying single-digit numbers together, right? Single digit times single digit. That's like, you know, multiplication flashcard kind of stuff for kids. That's helpful. Another benefit is that while I still have to do multiplication and addition, I'm doing them in completely separate points of the problem. All my multiplication is first, all my addition is last. So I'm not mixing that up. The other thing is that there's no mysterious 0 that shows up. Now, let's go back for a second because I talked about it in this funny way and this like as though it was magic, and I know you guys are smiling a little bit when I said it. Do we know why there's a 0 there? Because you're probably going to have to teach this at some point, standard algorithm too. So what in the world is there a 0 there for?
Does it represent half moving into the tens place?
Yeah, part of that. So it happened when I multiplied by the 3, right? But when I multiplied by the 3, I really wasn't multiplying by 3. What was I really multiplying by? 30, right? When you multiply by 30, there's an inherent 0 in every single part of that problem. That's why that's happening. So there is a reason for the 0 just showing up out of the middle of nowhere. But you don't have to even explain or worry with that with either of the other methods, right? Because there is no mysterious 0 that appears. So another thought. Okay, we had division. All right, we're ready to do division. All right, standard algorithm for division says that I put the 5 on the outside, and I put 623 underneath my division bar. And I probably ask myself something like this. How many 5s go into 6? And the answer is 1. So we write a 1 down here, and then we say, what is 1 times 5? And we get a 5. And then what do we do with the 6 and the 5? We subtract. 6 minus 5 is 1. And obviously, 5 doesn't go into 1, so the next thing I do is I bring the next number down. So now I've got the number 12. How many times does 5 go into 12? 2. So I write down a 2. 2 times 5 is 10. And then 12 minus 10 is 2. We're almost done with this, and I'm sorry, I was not keeping an eye on the clock. I apologize. We're almost done. We're going to bring the 3 down. 5 goes into 23 4 times. 4 times 5 is 20. And I subtract. And I get the 3. 5 does not go into 3 an even number of times. At some point when we move into decimals, we start looking at that. That's not the point where you first start with kids, right? And you don't do fractions either. The first thing you do is what? Do you remember? You do remainders, and you say R3 at the end. And that's where we are in this kind of a problem right now, like educationally, okay? So we're at the R3 kind of answer. All right, so we'll pause there for today.